Hi, I'm Ashley. I'm a researcher here at the University of Manchester. I'm currently in a nuclear sample preparation lab where I work on zirconium-uranium alloys with Rolls-Royce Nuclear. The atoms that make up everything around us are composed of a dense nucleus of positively charged protons and neutral neutrons, with negatively charged electrons orbiting around the outside. In 1938, Lise Meitner, Fritz Strassmann and Nobel Prize laureate Otto Hahn discovered that certain really large, unstable nuclei will decay by splitting into two, usually unequal parts. The splitting of the atom is called nuclear fission. The key to fission is the neutron, first discovered by Nobel laureate and University of Manchester graduate James Chadwick in 1932. When a nucleus splits like this, it usually also releases a couple of neutrons. There are certain nuclei, like uranium-235 and plutonium-239, that don't split in half spontaneously, but will undergo fission if they absorb a neutron. This reaction releases another 2 or 3 neutrons, and those can then be absorbed by another uranium or plutonium nucleus, causing another fission reaction and releasing further neutrons. Reactive isotopes like these are called fissile isotopes. Each fission reaction also releases energy. This chain reaction is the fundamental basis of nuclear power. With nuclear weapons, the aim is to maximize the amount of fission reactions in a very short time through exponential growth. However, for nuclear power, we want to keep a steady rate of energy production. So, for every one fission reaction, we want only one of the released neutrons to go on to cause another reaction. The first sustained chain reaction was accomplished by Enrico Fermi in 1942. Neutrons interact with matter in a variety of ways, but the 3 important ones are scattering, where the neutron hits a nucleus and bounces off, transferring some energy. Absorption with fission, where the neutron is absorbed by a nucleus and induces a fission reaction. And absorption without fission, where the neutron is absorbed by a nucleus but does not cause it to split. To maintain the steady-state stable reaction, we need to balance the neutrons that are produced with the neutrons that are lost in the system. If too many neutrons are produced, the reaction can get out of control, and so we need ways to lose more neutrons. If too many neutrons get lost, the reaction can die out, and so we need to make sure more neutrons stick around. So how are neutrons lost? First, they can fly out the sides of the reactor. Second, they could be absorbed by some other nucleus and not cause a reaction. Sometimes we do this deliberately by putting in control rods that soak up excess neutrons using a material that has a high chance of absorption. However, most of the time this needs to be engineered around. An example of this which relates to my work involves the choice of material used for what's called cladding. Most nuclear reactors have the nuclear fuel, containing fissile material, a coolant, and cladding material separating the two. In many water-cooled reactors, this material is usually zirconium metal, which has a very low chance of absorbing a neutron. As mentioned earlier, my work focuses on zirconium metal alloys. This graph shows the relative probability of a neutron causing fission in uranium-235 plotted against neutron energy. The scale is logarithmic, meaning each tick up the y-axis is 10 times bigger than the last. As you can see, U-235 is much more likely to absorb a neutron and undergo fission at lower neutron energies. The band shows the average energy of neutrons produced in a fission reaction. The trouble is, fission neutrons have loads of energy, too much to be absorbed easily. So how do we get the energy out of the neutron? We use scattering. Nuclear reactors that rely on slow, low-energy neutrons are called thermal reactors. In a thermal reactor, there is a material between the fuel rods that absorbs the energy of the neutrons before they enter the next fuel rod. This material is called a moderator. The neutrons scatter off atoms in the moderator, giving up some of their energy. Neutrons transfer only a bit of energy in each scattering reaction. so many collisions are needed to bring the neutrons down to low thermal energies. So in water-cooled reactors, the water that's used as the coolant also acts as the moderator. In other reactors, such as CO2-cooled advanced gas reactors, the moderator is made up of separate blocks of graphite. The problem with water is it easily absorbs neutrons. To counter this, we give the fuel a boost, enriching it in uranium-235. Natural uranium is made up of more than 99% uranium-238, an isotope that is not fissile and doesn't work well in most nuclear reactors. Less than 1% is the isotope of uranium we want, uranium-235. Enrichment is a process that increases the concentration of uranium-235 to roughly 5%. This higher density of fissile material compensates for the neutrons lost to the water. These are the fundamental challenges faced by nuclear engineers. We are on the cusp of creating new reactor designs to achieve the power needs of the future, designs that require innovation, research, and new materials to get them off the ground.